Okay, folks, good afternoon. Just a reminder that our quiz for Tuesday, 5 days from today, is going to be covering matrix converters. Any questions? Yes?
Are you going to want switch? I mean, which exactly switch type goes in the matrix?
You mean switch realization?
Mm-hmm.
Probably not, because that's a switch realization topic. It's not a matrix topic. So the quiz is probably a matrix converter, a particular output voltage is desired, then you have to figure out what switches should be on or off or things like that. Any other questions? Okay, so we are going to continue our discussion about power factor correctors. So what we did last time was, first of all, we defined mathematically what power factor is, which is the ratio between active power and apparent power. So in a simulation file, like if you are using MATLAB or Plex, there are blocks that are calculating power factor for you. But again, a piece of advice, unless you exactly know how a block operates, never use it. So what I usually do, I just use this equation over here when I'm trying to calculate a power factor. So there are two components important in the power factor. One is the distortion portion of the signal. So if our current is distorted from an ideal sinusoidal form or not. The other one is the displacement between the current waveform and the voltage waveform. If the input voltage is sinusoidal, our power factor equation is reduced down to this. And if the input current is sinusoidal and the input voltage, they are both sinusoidal, then it's basically cosine of phi, which is the phase angle between the voltage and the current. Then we looked at different ways of classifying power factor correctors. Like one is, if you have more than one stage of conversion, power conversion, you call it multi-stage or double-stage. And sometimes you are looking at a single stage power factor correction. Then we kind of got a feel about when we are looking at a power factor corrector, what does our input power look like? It's actually fluctuating with twice the line frequency, and our output voltage, because of that, is going to have a relatively large 120 hertz ripple. If you try to eliminate that ripple, but significantly eliminate that, your approach would require a very large capacitor, and it is not going to be better than a passive approach. So just get used to that power factor correctors always have 120 hertz on their output voltage. Now, is our load okay with that or not? If it is not, and by the way, the voltage in the output is usually larger than the peak value of the voltage in the input. So a lot of times you have another converter which is stepping down that voltage and also is eliminating these 120 hertz of ripple. Then we had a kind of a rough estimate, like a ballpark estimate of how to find the value for this C, the capacitor, the output or energy storage in general. And we ended up with this equation that the ripple, the peak-to-peak ripple in the output voltage is basically following this equation in which C appears. So if you're trying to limit the ripple in your output voltage, you can use this equation to find the right value of your capacitor. Just a reminder, omega is 2 pi times the line frequency, which is usually 60 hertz in the US. It is not the switching frequency. Then we try to find out with the classic converters that we are familiar with, what topology would actually suit our application. We realize that our voltage transfer ratio should have a minimum value, and then it should be larger than always minimum value all the way, ideally, to an infinite value. So between the buck boost and buck boost converters, you can see that the boost would be the best candidate for you, because in the boost converter, you can always have an output voltage that is larger than the input voltage. Another advantage that the boost converter has is that the input current is continuous, and continuous currents are always preferred compared to non-continuous current, discrete currents. Now, this does not mean that we cannot use buck or buck boost topologies for a power factor correction where there are limitations basically involved. For instance, for the buck topology, so let's say if this is your rectified input voltage and this is your kind of output voltage, you can see that your current, so buck is stepping down the voltage. So when you are in this region, you can step it down to the output voltage. So technically your current is pretty much zero when you're out of that portion, and then you can control the current like this. Okay? It's not a very perfect approach, but still it's doable, and then your power factor is going to be like hovering around, for instance, 60 or 70%. Same story for the buck boost. Technically, any converter could be used as a power factor corrector, but boost seems to be the most promising one. And again, remember that if you're using the boost topology, your output voltage should be larger than the peak value of the input voltage. Like here in the US, the voltage is 110 volts RMS times 110 times the square root of 2, somewhere around like 155 or 160. So your output voltage should be larger than that, for instance, 200 volts or something like that. All right, so any questions? Okay, so we're going to move on to the kind of a different ways of using this boost. So boost topology by itself seems to be a promising choice. Now the next question is, how can we control this boost? So there are different ways of operate and control the boost topology. So let's talk about boost power factor corrector, and this is operating at a constant frequency. I mean switching frequency. And it is also operating under DCM, discontinuous conduction mode. So far in this class, we have been trying to avoid DCM, but this is pretty much one of the most common basically applications for the DCM, and we are going to see what it is. So technically, you have your source, your AC source. Then immediately after that, you have your bridge of diodes to kind of get the absolute value of this AC source, and then you have a boost. So let this time use a MOSFET. All right, so something like this. And the simplest way of controlling this boost is to turn the switch on and off at a constant frequency, and then keep the on time of the switch constant. So let me write it over here, constant T on. So there's a controller here. Remember, we still would like to regulate our output voltage. So we are still measuring the output voltage and compare it with the reference, and there's a compensation network involved. And then we decide how much the value of T on should be. So this controller determines whether T on should be 10% of the duty cycle or 20% of the duty cycle. 10% of the switching period or 20% of the switching period, whatever that is. So it's quite simple. If you look at IL, so let's just say this is one of our switching cycles. Okay, it's operating at DCM. So we turn the switch on at the beginning of the cycle. So the inductor current ramps up linearly. In this mode, it's actually the source that is energizing the inductor. Then the value of T on is determined by the controller. And then after T on arrives, you just turn the switch off. And then wait for the next period to start. All right, something very, very simple. This period is also called TD, primarily because it's the diode that is on during that time. So they call it time for the diode, or T sub D, or something like that. All right. So my argument is, if we follow a simple logic like this, you are going to achieve, to a certain extent, a good power factor basically in your inductor current. So we are going to see why. I have a simulation file already posted on Blackboard. So we're going to see the simulation file, then come back and see why it is that it is doing what it is doing basically. Before we get there, just a general, some general notes about DCM, discontinuous conduction mode. There are advantages and disadvantages associated with it. For instance, one advantage is when you turn the switch on, the current of the switch starts from zero. So you have like a zero current switching going on over there, which is good. And we haven't talked about soft switching yet, but this is going to be our last topic after PFCs are over. So we realize that whenever you turn the switch on or off, if the current of the switch is starting from zero or returning back to zero at the very same time, it's good. That means your current doesn't jump, there is no DI over DT, there is no EMI noise, it doesn't couple with the leakage inductances and things like that. The other good thing about this approach is we are controlling the current, but we are not even measuring the current. So very simple. You don't even need a current sensor. What you do is indirectly controlling the current. So we are kind of doing a current mode control a little bit, but we are not even measuring the inductor current. So no inductor current measurement. Okay, so let's take a look at the simulation file. Okay, so over here I have this boost topology. It's in MATLAB. It's in Simulink. It is not in Plex. So this is my sinusoidal source. It is rectified. Rectification is basically getting the absolute value of a signal. That's rectification. And then when the switch is on, this is controlling the switch basically. When the switch is on, we have Vn is applied to the inductor. When the switch is off, we have Vn minus V out. So if this is V out, then it is being subtracted from V in, and that's actually the voltage of the inductor, and the inductor value is 16 microhenries. Is still a relatively small inductor, and we are going to actually play around with this inductor to see what happens if we not do a good job in terms of selecting the value of the inductor. This once you have the inductor current, then inductor current times the status of the switch gives you the diode current, and the diode current minus the kind of load current is the capacitor current. And then once you have the capacitor current, You integrate it to find the voltage of the capacitor, which is your output voltage. So we have seen this before. The value of the cap is 1 millifarad. So in the simulations that we had before, when we were looking at DC-DC converters, this output capacitor was usually around 10 microfarad or 20 or maybe even 50. But here it's like 1,000 microfarad. So you can see it's a relatively large capacitor because we are trying to eliminate or reduce the 120 hertz ripple in the output voltage. So this is it. As long as the output voltage is concerned, there is no controller. I don't even have a closed loop basically feedback. All I have is I have a switching frequency of 100 kilohertz and a pulse width of 28%. Like my T on is 28% of 10 microseconds, 2.8 microseconds, something like that. So let me just run it. Okay. So here we have 3 graphs. The top graph, the top trace is your output voltage. First of all, note that the design has been good and the output voltage is larger than the peak value of the input voltage. If your input voltage is 110 volts RMS, let me see if it is 110. Yeah, 110 times the square root of 2 is the peak. Then your output voltage should be at least about 180 or 200 volts, and it is here about 240 volts. So that makes sense. So this is 240. The other thing is you can note that the ripple, the 120 hertz ripple in the output voltages, even though we have used such a large capacitor, it is still noticeable. You can actually see it. So the output voltage is fluctuating between 236 all the way to maybe 249, almost 9 or maybe 10 volts peak to peak ripple. Okay, so we are okay with that. The bottom trace is the output power. Again, I just wanted to remind you guys that the output power is relatively constant. In our case, depending on the value of the load resistance. In our case, it is about 680 watts, but it is fluctuating. So this is actually in agreement with what we had last time in terms of the output power. Remember, I drew output power like this. This is exactly like that. The middle trace is the inductor current. If you don't zoom in, if you just look at the envelope, actually it is following some sort of a sinusoidal, rectified sinusoidal version. Remember, this is actually just the inductor current. It is not the input current yet. So right now, we are looking at this current. Once this current reflected to the primary side of your bridge rectifier, it's like doing the opposite of getting the absolute value of the signal. Half of it is positive, the other half is being multiplied by a -1. So if you actually are curious about the waveform for the input current, I have it, I do not actually draw it. Let me see if I have an IN waveform. Yeah, actually I have it here. Our input current waveform is this kind of purple waveform over here, okay? So it's bipolar, it's almost sinusoidal. The envelope is almost sinusoidal. All right, going back over here, now let me zoom in. You can see that the inductor current is in a DCM, discontinuous conduction mode. This is the beginning of the cycle. You turn the switch on. It goes to a particular value, and then T on arrives, which is 28% of the period, and then you turn the switch off, and it goes down. This actually, when we are designing the power stage, so this is actually when the input voltage is very small. You can see that you only have like a little bit of a spike of current, then a long portion of no current at all, and then the next cycle arrives. So if you do not do a good job in terms of designing the inductor value, So if your inductor is, for instance, too large, you may actually go into continuous conduction mode. So let's try that. So if you are trying to design the inductor, remember we had an equation for the boost converter. L has to be greater than a particular number. In that case, you should, when it comes to plugging in your input voltage or output voltage, like when it comes to input voltage, you have to put the peak value of the input voltage, because that is when you are more likely hit DCM that you're trying to avoid. So let's make the inductor 10 times larger. Okay, so already in DCM in this. Okay, so it's something like this. It is still functioning like a boost. Your output voltage is about 210 volts with a lot of ripple. And the pattern of the inductor current is very weird. It's actually gone into CCM, which we were trying to avoid. So you can see that there is a CCM going on over here. But when the input voltage is small, it's crossing 0, you are still in DCM. So worst case scenario is your input voltage is very large. It's close to its peak value. So when it comes to calculating L, you should consider peak value of your input voltage to make sure you are in CCM. You are in DCM. All right, so let me make this a little bit smaller. The other thing that we can play around is the value of this cap. It's 1 milli. Let me make it 10 milli. Obviously, the system is going to get sluggish. It's going to take a while for this cap to get fully charged. I have used a larger capacitor. Therefore, my output voltage ripple is smaller. Before, it was like 10 volts peak to peak. Here, it's only like 1 volt peak to peak. It's like almost proportional. I made it 10 times larger. The ripple got 10 times smaller. And this is in agreement with this equation that we had. So I make this capacitor 10 times larger, the ripple got 10 times smaller. So almost a linear relationship. But again, remember, large capacitors are not necessarily good because we don't actually show the transition over here. But it takes a while for this capacitor to get charged, and it's bulky, and you have to pay more money to buy it. It depends on basically the customer or the design, how much ripple is okay with them. So let's say our customer is okay with 10 volts of ripple. All right, the other thing that I have done over here, down here, is it was easy for me to use one of those little blocks that gives you PF power factor, but I didn't do that. I'm just going with the conventional definition of the power factor, which is the ratio between average power and the apparent power. And what was the apparent power? The RMS value of the current times the RMS value of the voltage. So here I'm multiplying Vn and In to get the instantaneous value of the power, and then apply a low-pass filter to give me the average value of the power. And then I'm multiplying Vn by itself, and then the low-pass filter and a square root. This is the RMS value of the input voltage. Even though I had it, it was like 110. And then also I'm doing the same thing for the input current to get me the RMS value of the input current. Then in the end, it's just a division between them. So looking at the power factor, you can see, well, obviously my calculation is not absolutely good because of the low-pass filters that I have used. But it gives you a rough estimate of our power factor is about 70%, maybe 68% or something like that. So not bad, because if I get this boost out of the way, my power factor might be as low as maybe 40%, because it's just a bridge rectifier with a very distorted current waveform. Okay, let's take a look at this one now. So this one is comparing the waveform of our input voltage, which is the yellow one, 110 volts times the square root of 2 is this peak, about 155. The red one is the actual input current. Again, if I zoom in, I'm going to see that it's kind of a discontinuous thing. And the blue one is if we apply like a low-pass filter to the input side to kind of eliminate the high-frequency ripple and just give us the moving average of the input current, you can see the input current is actually not, on average, it is not sinusoidal, but it's okay. I mean, it's at least in phase with the input voltage. It is trying to be sinusoidal, and but this is the best we can do with such a simple approach. One thing that I can show to you guys is, okay, let me zoom in and show. Okay, we don't really have to zoom in here. It's just a low-pass filter. But the whole thing is this low-pass filter, see how small this number is over here. It's like 50 micro. That means the filter that I'm using is just trying to eliminate the switching frequency ripple. So if you really want to implement this filter on the input side, the capacitors or the inductors that you need to use are relatively small because they are trying to eliminate 100 kilohertz. All right. The only thing that we haven't played around so far with is T-on time of the switch. So let's take a look at that. So now let me increase the duty cycle or on time. Instead of 28%, let me do it, I don't know, 50%. Okay? So 50% is, if I go back to this node, so before what I'm doing is okay, this is one period, and this is 28% of that. So inductor current rises, falls, and then 0. Now I'm actually increasing it to 50%. So inductor current rises, falls, and 0. Okay. First of all, you can see that, first of all, we have to worry about going to CCM again because I'm keeping the switch on for a longer time. It's more likely for me to go to CCM. The other thing is you can just compare these two graphs and see the bottom one, on average, my inductor current is larger. So it's like I'm getting more power from the source. So I'm expecting that my output voltage to be larger because it's an open loop basically system. So these are our expectations. One, we have to worry about not going to CCM, going to CCM, and the other one is my output voltage was before like 240 volts. Now I increased T-on, so it's probably going to grow larger. All right, so let's check the. Okay, so see at the very beginning, the voltage. Actually, if you go to CCM, but the inductor is small enough, so you don't have to worry about it for now. Although I have to double check and make sure we are not actually in CCM. You can see we are relatively close, almost at the critical point, but we are still in CCM, so we are still in DCM, so that's good. And as I had expected, my output voltage is larger because I'm actually providing more power. It hasn't actually settled yet. Before it was 240 volts. Now it is 350 volts. Again, it is still larger than the peak value of the input voltage. And because of that, my output power is larger now. It was, I don't know, 680 watts. It's now 1400 watts. Now what's interesting is if I look at power factor, my power factor is going to be a little bit better. Before it was about 70%. Oh, it's actually worse. Well, we have to look at that. Maybe it hasn't settled yet. But let me look at the inductor current waveform. You can see the pattern of the inductor current is a little bit changed a little bit. It's got a little bit better. So I was actually expecting my power factor to be better, but I don't know why it is not. Maybe I just have to run it for a longer time. Make it a little longer. Okay, it hasn't settled yet. I don't know what happened, why it stopped, but I'm expecting the power factor to be actually a little bit better. And actually the paper is predicting that it is supposed to get better. So maybe I posted this on Blackboard. Maybe you guys want to play around with it and see if it actually gets better or not. All right, so we saw the simulation. Now let's go back to some theory and see why this is functioning the way it is functioning. Okay. Any questions so far? Okay, so the reason that it is functioning this way is quite simple. So let me just show I, L, peak. Okay, so I'm actually talking about this peak of this point over here. The peak value of the inductor current. And remember, the inductor current is not really the input current, okay? Inductor current is the absolute version of the input current, absolute value version. So going back to the operation of the boost converter, remember when we turn the switch on, the input voltage is applied across the inductor. And so technically this gives us the rectified version of the input voltage and divided by the value of the inductor times the duration that the inductor is on, which is kept constant of T on. And remember, the input voltage is sinusoidal, so it has a maximum value times okay. So as you can see, the inductor value is constant. So this term is constant. This is almost constant. Peak value is like 110 times the square root of 2. We are keeping T on constant. And so technically you can see that the peak value of the inductor current is proportional with some sine function. So that's what we wanted. I mean, we wanted the inductor current on average to follow a sine, but here is the peak value that is following the sine. So the conclusion is the peak value of the inductor current is almost sinusoidal, or a rectified version of the sinusoidal. And that was very easy to observe. That was one of our first observations. If you look at the envelope of the inductor current, you can see it's like almost following a rectified version of a sine function. Also, as we saw in the simulation, T on, if you play around with T on, actually we can actually regulate the output voltage or determine how much power is being delivered to the load or how much current is drawn from the source. So T on is constant. It determines P out, or maybe V out. Okay. Okay. Now, when we were looking at the average value of the inductor current, or maybe the input current, it wasn't really sinusoidal. So when we were looking at this average value, you can see that this blue kind of a curve is not really sinusoidal. So let's take a look at this and see what is determining the distortion in this waveform. Okay, so I'm going to draw the current one more time. So if we focus only on one switching period okay, so we are looking at if I look at IL average value, okay, it is basically the area under this triangle divided by a switching period. So we are looking at IL peak, which is the height of this triangle, times T on divided by 2 divided by the switching period plus IL peak times TD over 2T. Okay, so I'm actually looking at the area under these two triangles. One of them is this triangle, the other one is this one. Okay. So now I'm trying to eliminate TD, the conduction time for the diode. So if you want to eliminate that, you can write it this way. The peak value of the inductor current is the input voltage over L times T on. Okay. At the same time, if you look at the second mode of the boost operation, it is the output voltage minus the input voltage when the diode is conducting divided by L times TD. Okay. So this is looking at mode 1. When the inductor is being charged or energized by the source and the switch is on, and this is mode 2 when the inductor is being de-energized through the diode and delivering energy to the load. So this gives us an expression for the TD. The conduction time of the diode is Vn over Vout minus Vn times T on. Okay? So what I'm going to do now is I'm going to place this TD over here. Okay, so let's do that. And also, instead of IL peak, I am going to put what I had over here. This expression goes for IL peak here and also here. And I'm going to simplify it a little bit. Times T on D is the duty cycle. And then I can maybe further simplify this equation, assuming that I determine or define alpha as as the peak value of the input voltage divided by the output voltage. Remember, this is less than 1 because we are using the boost converter. And also, if I define K as a constant parameter of duty cycle squared, switching period, output voltage divided by twice the inductor. So in this, under these two assumptions, the average value of the inductor current will be an expression like this. Okay, it's just defining a parameter. So you can see that the moving average of the inductor current is not sinusoidal, but it has sine terms in it. And if magically I eliminate this portion, it will actually become sinusoidal then, because it's going to be just K alpha times the sine signal, basically, okay? However, because what we have in this red area that I have encircled, your moving average is going to be dependent on the value of alpha. So if this is an ideal sine function, if I plot what I have on the screen, it is going to look like something like that. That's what we saw in the simulation, basically. So this is, for instance, alpha is large. Okay, let me say, for instance, alpha is 0.9. But if I make alpha smaller and smaller and smaller, this portion will be smaller and negligible compared to 1. So I'm expecting to get closer to an ideal sine form. So for instance, if alpha is for instance 3, I get something like this. Okay, so smaller alpha would actually make the situation better. What is alpha defined as? Alpha is the ratio between the input voltage peak and the output voltage. So in order to have a smaller alpha, I need to have a larger and larger output voltage. Okay? So basically, if I try to boost the signal as high as it is possible, physically and practically possible, I will get closer and closer to an ideal power factor correction. So I was trying to show that actually in the simulation. Unfortunately, it didn't work. Let me give it another try. This time, instead of playing around with T on, let me play around with the value of the load resistance, because they both have the same impact. So let me do this 28%. All right, if you remember, this was about 70% power factor. Okay. Okay, let's call it, yeah, almost 70%. Now let me increase the load resistance. So I'm increasing the load resistance. It's an open loop system. The reference for the current hasn't changed, so I'm actually expecting my output voltage to be very large. Under previous load value, the output voltage was about 240. Now it's probably going to be much larger. It is still growing. First of all, I increase the load so I don't have to worry about going further into CCM, because it's the opposite way. It's actually we are going further into DCM. But let's look at this power factor now. Okay, for some weird reason, it's actually going down, and I have to investigate that and see why that is, because I'm actually expecting my current to be closer to a sinusoidal form. Let me see. Maybe not. So let me further investigate this later. Probably we cannot. Yeah, it looks better compared to the previous case. It's almost getting close to a sine case, but I don't know why my power factor is not actually showing any improvements. Maybe my filters are not designed well. Anyway, there is a paper, and we are going to go through this paper very quickly, but the paper's prediction is if you plot power factor versus alpha, which is V in peak over V out, you get something like the best power factor is obviously 1. You get something like this. Let me try it again. Obviously, alpha is not supposed to get larger than 1 because it's the boost converter. The output voltage is always larger than the input voltage. And you get something like this. All right, so something like that. Unfortunately, my simulation does not show that. But you can argue that if alpha is very large, TD gets very small, and once TD totally is eliminated, if this area is eliminated, this peak was proportional with the sine function. Therefore, you are actually looking at the average value that is also proportional with the sine function. Now, taking at the, so let me write it down here. Alpha large. I'm sorry, alpha is a small. V out is large. Therefore, TD is a small. Therefore, IEL on average is almost the same as a sine function. Okay. This paper is also uploaded on Blackboard. In case you are interested, take a look. It's a very simple, straightforward paper. No, this is not what we're looking for. Oh, here it is. Okay. So the simple math that we went through is coming actually from the paper. So if you want to have more references, you can take a look at it. So this is the chart that I was just trying to draw on the board. So if alpha depending on what the value of alpha is, remember alpha is determined by the value of the output voltage. Depending on basically what the value of your output voltage is, you're looking at an average inductor current that is, in case number 5, it is kind of distorted. Alpha is 0.9. It's supposed to be smaller. And then once you make the output voltage larger and larger, and then alpha gets smaller and smaller, then your current gets closer and closer to an ideal sinusoidal form. For instance, case 2, alpha is only 0.3, and you can see that it is almost similar to case 1, which is the ideal sinusoidal form. The other graph that is actually important that, again, I try to draw it on the board is power factor versus alpha. So if alpha is very small, your power factor is actually doing quite well. If alpha gets large or the output voltage gets small, then your power factor starts actually declining. All right? Although my simulation doesn't show this, so I have to actually investigate and see what is going on in my simulation. Maybe it's just the way that I'm calculating the power factor is not very fast. All right, any questions? So remember, a small alpha is good from the perspective of a power factor improvement, or a large output voltage is good, but then you are going to face some other challenges. For instance, your output voltage is too large. That means the stress on your switches is too large. Like you have to pick a switch and a diode that can handle a very high voltage, and then the switching losses are going to go and actually an increase. And you need a capacitor that can handle a larger with a higher voltage rating. So you can see that it's always a compromise. Any questions? Yes.
So if you needed a lower output voltage, you can implement a flyback converter with a buck?
You mean lower than the peak value of the input voltage?
Right.
In a double stage case, you can actually cascade another buck converter after this to step it down from like 240 to something else. But let's say if you want to do a single stage, you can do a flyback. Although the problem with the flyback topology is that the current, the input current is not continuous. Although yes, there is a lot of applications you are using flyback as your PFC, because in addition to power factor correction, it also provides isolation, which is good. Or you can use even a buck converter. As I said, your current is a little bit, your input current is distorted, but hey, what can you do? This is the best that you can do, which was, where was that we were drawing that? So you can even use a buck converter, just a direct buck converter to just step things down. But when your input is smaller than your output, then the buck doesn't function, therefore your input current is almost zero. So input current distortion is relatively high. Other questions? All right. So this was the simplest way of doing power factor correction. It's quite common for a variety of reasons. First, we don't even need to measure the inductor current, which is great. We don't need a current sensor. The control algorithm is very simple. Just keep the on time of the switch constant. And you only have one switch and one diode. It's actually very, very simple. Although there are disadvantages associated with this, and that is the disadvantages that are always associated with DCM. And that is, for a portion of time, there is no current. For a portion of time, we are not actually using the source technically. So you're actually using the source only during T on. Beyond that, the source is not being used. So you are not effectively using the source. And therefore, if you want to deliver a certain amount of power to your load, the RMS value of the current is high. What do I mean by that? So let me show it over here. So the inductor is operating in DCM. Therefore, high RMS current. Okay, so what we mean by that is, if you let's just focus on one period. Your objective is to deliver, I don't know, an RMS of 2 amps to pass it through the inductor. You can use it this way, or you can use it in a continuous way, this way. Okay? If you try to compare these guys, you're going to realize that your peak in the DCM is much larger than the peak over here. Even though they have identical RMS values, because the top waveform has a section that it is 0, to compensate for that 0 portion, your peak inductor current should be much larger. All right. So that means if you're delivering power to a particular load, you better have a continuous current instead of a DCM current that is sometimes zero, nothing basically. And RMS is larger, therefore the losses, the conduction losses are going to be larger. Okay, so efficiency is going to suffer. Okay, so you may say, okay, I don't want this DCM, I want CCM. But once you go to CCM, all the logic that we talked about is not effective anymore. So you may want to say, okay, I want to avoid DCM as much as I can, or in other words, go to the critical conduction mode. So okay, so solution would be, so we still need DCM. I'm sorry, we need. So solution would be critical conduction mode. So in the critical conduction mode, we are trying to eliminate that zero portion that we are not even using the source at all. So what we do is you turn the switch on, the inductor current rises, then turn it off, and then as soon as it turns back to zero, you turn it on again. Okay, something like this. All the logic that we explained, that the peak value of the inductor current is proportional with the input voltage is sinusoidal, therefore this peak is sinusoidal, and the PFC is going to happen. All of those are still valid at the same time. You are trying to make sure your inductor current is, the RMS value of the inductor current is as small as possible under a particular power rating. Although there's going to be another problem presenting itself, and that is your switching frequency is not constant anymore. Okay, so if this is your input voltage, okay, when the input voltage is small, your switching frequency, your switching period is small. When your switching frequency, when the input voltage is large, your let me draw this in a better way. All right, something like this. So you can see that now your switching frequency is not constant. So you try to solve a problem at some point, you're adding more problems in other places. So this approach, the critical conduction mode, there are advantages and disadvantages. One is, one disadvantage, a variable switching frequency. So you can easily say that this period is much smaller than this period. So as your input voltage grows, your switching frequency goes down. Although we did this to get some advantage, and that advantage was a lower RMS value. Okay. And there is also another disadvantage. Can somebody think of that disadvantage? The logic that I said, the inductor current returns back to zero and you turn the switch on. Anybody?
About noise.
Noise, okay. But even before noise. Zero switching. So you have to monitor the inductor current and to see when it comes back to zero, okay? So you have to basically measure the inductor current. When it comes back to zero, you have to turn the switch on. That means you have to monitor the inductor current. We have to measure the inductor current. Okay, I mean measurement, but honestly, all you care about is how close your inductor current is how close your inductor current is to zero. Okay, you don't really need the absolute value of the inductor current. Just is it getting close to zero or not? But still, that's kind of a measurement, so you have to kind of measure it. And yes, you're right. So once you do that, then the noise comes in. Okay, how much noise is riding on the signal that I'm reading? Is it accurate or is it not accurate? So this particular one is called variable frequency DCM boost. Okay.
Does this variable frequency DCM boost has a better power factor than the
I would say almost the same, because power factor is a function of this portion of the signal, and they haven't changed much. So I would say they are almost the same. Variable switching frequency, in case you don't know why it is a bad thing, it is because once you have your switching frequency fixed at a particular number, if you have noise issues and EMI issues, you are going to design all the filters based on that frequency. But now the frequency is variable, so you have a very broad electromagnetic interference spectrum. Okay, any questions? Yes.
Since we are measuring the current to control the switching frequency, is there like an extra components control?
So yes, so your logic is you have to monitor at least the polarity of the inductor current or see how close it is getting to zero. Probably there's a flip-flop over there and some measuring system. Then the flip-flop is going to get set. That means you're close to zero. Turn the switch on or start a new cycle, and then keep it on for T on, which is a constant, basically T on. So yeah, there is some extra analog circuitry, or if you are doing in a DSP fashion, digital fashion, an extra logic in the system. So remember, this is a still constant T on. The T on is still constant. All right. Any other questions? Okay. So these are the simple discontinuous conduction mode boost operation. Now, that doesn't mean we necessarily have to do DCM. We can also do CCM, which we are about to actually take a look at. So the next thing is okay. So instead of running the converter at discontinuous conduction mode, run it at continuous conduction mode. And one of the topics that we have studied before was current mode control. So remember, in power factor correction, you're trying to form the waveform or the shape of the waveform of your current. Well, if you know how to do current mode control, you can actually provide a reference for your current that is sinusoidal, and then force the inductor current using the current mode control techniques that we are familiar with, force the inductor current to follow that particular pattern, okay? So obviously boost, we are still using boost because it gives us a continuous input current. Output voltage is larger than the input voltage, but at the same time, we are using our, for instance, peak current mode control technique to form the inductor current. So looking at the diagram now, let me call it, for instance, peak current mode control. All right. So the diagram that we are looking at, let me see if I can find it. So we are still using this boost topology. Here we have our bridge rectifier. We just draw it. How do you draw a bridge rectifier? Let me draw it this way. Let me just not draw it, because definitely I'm going to make a mistake and then. Okay, something like this. So remember, we are looking at current mode control. The most common one that we have used before is peak current mode control. So let me draw a peak current mode control block here. Okay, remember, for the peak current mode control, you had like a reference for your signal. And that reference before, when we were working on DC-DC converters, it was coming from our voltage compensation network. All right. So, so let me see, call it IREF. Or let me, okay, the bottom one. Let me call the bottom one IREF. And then somehow we needed to have information about the peak value of the inductor current, meaning that either we have to measure the inductor current or the switch current, doesn't really matter. Let's just measure the inductor current. So if you remember from before, the way this peak current mode controller functions is, at the beginning of the cycle, there is a clock that sets a flip-flop. So your cycle starts, you turn the switch on, then whenever the inductor current tends to get larger than the reference, it resets that flip-flop or latch, and then the transistor or the switch turns off, something like that. All right. So the output is easy, it just goes to the gate. All right. So, and remember, we had to have some external ramp to avoid that subharmonic oscillation problem. All right. So the question is, where is this reference coming from? Okay. So remember, we would like our reference to be something like this. Okay. So some sort of a sinusoidal signal that is rectified so that our inductor current should follow almost the same pattern. So the best idea is our voltage here could be used as a reference, or something proportional with the voltage could be used as a reference. So let me measure this voltage. So we have some, I don't know, 1 over, let me call it K in. So one of the components that forms our reference for the current is the shape or the waveform of the input voltage, because we want the inductor current to be proportional with the input voltage. The other input comes from regulating the output voltage, or basically how much power do we need, or we are trying to keep the output voltage constant. So we have to measure the output voltage as well. So there is a measurement gain here too. And a compensation network. So we kind of have several loops over here. One loop is measuring the inductor current, and that is basically this loop. So this loop is because we are doing peak current mode control. We have to measure the inductor current, compare it with the reference, and then make decisions based on that. The other loop, we have seen this before as well. Measure the output voltage, compare it with the reference, get the error, pass it through the compensation network, and determine the level of your reference, basically, okay? So this loop is trying to regulate the output voltage. If the output voltage is smaller, send more current. If the output voltage is larger, send less current. The extra loop is kind of a feed-forward loop, which is trying to make sure our reference is kind of proportional with, in terms of shape or being in phase, proportional with the rectified version of the input voltage. So in terms of these signals, what should they look like? This is the output of a voltage compensation network. So it's almost like a very flat signal. And this is the measured version of the input voltage, so it's actually sinusoidal. Something like this. All right? Any questions? So remember, this peak current mode control has external ramp too. All right. I have a simulation file, and we are going to take a look at it. And it is posted on Blackboard, so until next week on Tuesday, I would encourage you guys to run this and become familiar with it. All right, so this is the model. Again, I have it in Simulink. This was developed before even Plex existed. So this is my power stage. This is the input voltage, 110 volts RMS at 60 hertz. And then I rectify it, just get the absolute value and ideal form. That's a rectification. And then the rest is our boost power stage. I'm still using that 5 millifarad capacitor to kind of almost attenuate the 120 hertz ripple in the output voltage. But because I'm expecting this to function at CCM, my inductor is much larger than the one we were seeing earlier. How much was it before? It's 360 now. I think it was like 20 or 30 here. 16. So you can see that my inductor is like 20 times larger. So because here previously I was trying to function always under discontinuous conduction mode. Here I'm trying to function always under continuous conduction mode. So this is the power stage, and the controller stage is down here. So measure the output voltage. There is a sensing gain involved, and output voltages are usually high. So you're stepping it down, let's say 20 times. And I'm trying to regulate my output voltage at 200 volts. So once I step it down 20 times, it should be hovering around 10. So my reference is 10. Comparison, error, compensation network. We will talk about where this thing comes from. And this is my measured input voltage. Again, there is a sensing gain over here as well. My input voltage can be as high as like 160 volts, but my analog circuitry maybe can handle some voltages between 0 and 15 or 0 and 5, for instance. So I'm actually stepping it down. Then I'm multiplying them by each other. So this is almost a DC signal, tells us the level of the current. This is an AC signal, proportional with the input voltage. So once they are multiplied by each other, it gives me the reference. Then the rest is the peak current mode controller. Measure the inductor current. There is a measuring gain as well involved. There is an external ramp, which is built over here. There's a clock, set and reset. So basically your external ramp is basically just jumping up and down like a triangular waveform. And this is the main latch. At the beginning of the cycle, which is determined by this clock, you set it so the switch is turned on. How do you reset it? You reset it when the inductor current tends to get larger than its reference. So that's the logic behind peak current mode control. Okay. And then the rest of the blocks are basically measurement blocks. So I would encourage you guys to take a look. I think I already ran this, and my power factor, no, unfortunately, let me just run it really quick. I think the power factor should be around 90%. Oops, it's not, okay, it's still running. Well, let's wait. Yeah, it takes time to settle down, but it's about 95%. So you can see that you're doing a better job. Your input current is looking a lot like the way it is supposed to look like. So we're going to take a look at this next week on Tuesday. All right, see you guys on Tuesday.